So typically, although not always, we frequently think of a set of parametric equations as tracking the motion of a particle in the xy plane over time. Or when you take, I think 21C, you can track a particle in 3 space, in the XYZ coordinate system. So often that's kind of what we think of. We track a particle as time flows forward. So let's look at this example. I'm writing the number 1 there. Is this my good pen? I got new pens, but you know how it is with the pens. They just go so fast. So let's say we have these parametric equations. X, and you can either write x or x of t. X of t is equal to t plus 2. Y of t is equal to t squared. And so, and we're also going to be given some domain restriction on t. T is between -2 and 3. And I would like to graph this. Now, we could do it point by point, right? We could say, we could make a chart of t, x, and y values. And you know, we could pick lots of numbers. We would probably stick with just the integers like -2, -1, 0, 1, 2, and 3, since t is between -2 and 3. And then find the corresponding x and y values. The x values will be, let's see, so it's just t plus 2. So just add 2. So 0, 1, 2, 3, 4, 5. And the y values would be t squared. So 4, 1, 0, 1, 4, 9. And then we can plot these points. One, two. So, right, we can plot the point 0, 4, and the point 1, 1, and the point 2, 0, and 3, 1, and 2, 4, and 5, 9. And so it looks like this. It looks a lot like a parabola, or at least part of a parabola, and that's because it is. We also typically, when we draw these things, we kind of draw arrows that go in the direction of time moving forward. So right here is time equal to -2, and then time equal to -1, time equal to 0, time equal to 1, time equal to 2, time equal to 3. So we would definitely draw little arrows along this graph in the direction that time is increasing. Now, you might recognize it's pretty inconvenient to plot a bunch of points. So often what we do to graph the thing in the xy plane is to eliminate the parameter t and then find the corresponding xy equation. So we could totally, in this system here, we could solve for t, and usually you want to just pick the one that's easier to deal with. So I'm definitely going to isolate t in this first equation. So I'm saying, okay, t equals x minus 2. And I'm going to substitute that in for t in the other equation. So y equal to t squared is going to become y equal to x minus 2 squared. And that's exactly the graph we have, or at least we have a piece of that graph. Right? We have the piece of this graph between x equals 0 and x equals 5, which is the same as being between t equals -2 and t equals 3, right? If t is between -2 and 3, then t is equal to x minus 2, then x minus 2 is between -2 and 3, and you can add 2 to everything to get 0 less than or equal to x less than or equal to 5. So often, although not always, but often if we're trying to graph a parametric curve, we typically, if we can, try to take our equations, eliminate t, and then write an equation involving just x and y that we're able to graph. So that is often our plan of attack. Let's look at some examples here. Some examples that are kind of the same, but a little different. And again, if you have and don't worry, we're going to get to the derivatives and second derivatives and the area and arc length and all that good stuff. We just have to kind of start with the beginning. So let's look at this next set of parametric equations. X equals e to the t, y equals e to the 2t, and t is greater than or equal to 0, which is often a condition for time, because often we say we can start at time equals 0 and we'll let time move forward. So I think this one's not too challenging to get, but y is equal to x squared, right? We could say, so here I probably actually wouldn't solve for t. You certainly could, but it's easier to just observe that y is equal to e to the t quantity squared. And then if we plug in e to the t equal to x, we're going to get y equal to x squared. Or you can make it more complicated. You could say t equals the natural log of x, and then plug that in for t there, so that then y is equal to e to the 2 natural log of x, which is e to the natural log of x squared, which is x squared. That's more work. Try to do less work. So if you see something that seems kind of obvious, you're like, oh yeah, I can just replace e to the t with x, do that. Now we have to be careful with our graphs, right? Because you might be mistakenly wanting to graph all of y equal to x squared. Which looks, kind of like, there's all of y equal to x squared. The problem is, our domain is restricted. In fact, I'm going to show you actually two different domains. So let's do t equal to 0 in blue, or sorry, t greater than or equal to 0 in blue. And let's say t can be anything in red. So t has to be greater than or equal to 0. What's the smallest x can be? What's the smallest e to the t can be if t can be as small as 0?
1.
Yeah, exactly. So the smallest x can be as 1, and the smallest y can be as 1. So this one, we actually only get everything from here, and then we move this way. So really, we shouldn't have any of this. So we start at the point 1, 1, and we just move up into the ranks. And 1, 1 is when t is equal to 0. Okay. What if, on the other hand, though, we did everything from minus infinity to infinity? Well, then, so if t can be all the way down to minus infinity, what's e to the negative infinity getting really, really close to?
Would it be like 1 over really, really big number? So
Well,
like
1 over e to the negative t. And if t is going to negative infinity, negative t is going to positive infinity. E to the infinity is really big. 1 over really big is really, 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 really close to 0. So for this one, you'd be almost getting all the way to 0. So it looks like this. Or again, you're going this way. So it's interesting that getting all the negative values for t only gives you this little section from here to here. Kind of neat. But more generally speaking, when you graph a parametric curve, you often don't get all of the curve that you would think you would get from the xy equation. Right? You have to think about, how is t limiting my values? So often what I would do is I'd say, okay, well, if t has to be bigger than equal to 0, if I solve for x, or t as a function of x, that means, okay, if t equals natural log of x, then natural log of x has to be bigger than or equal to 0, which means x is bigger than or equal to e to the 0, which is 1. It's really more of a, like, I really don't solve equations like that. I really just more use common sense, like, oh yeah, if t is bigger than 0, then x equals e to the t is bigger than 1. Let's look at another similar yet different example. And again, we'll give ourselves 2 restrictions on this one as well, just to kind of see. what if we have x equal to sine of t and y equal to, let's make it more interesting. Let's make it 1 minus, sorry, not that. Let's make it cosine squared of 3. I keep grabbing my less good pen. Okay. So I'd like to write x and y without the t's. Anyone have any bright ideas about what I could do with this, maybe?
Like arc sine?
Not so that is a good idea, but it's more complicated than I want to make it. So you're right. We could totally say that t is the arc sine of x, and then we could plug that in there and say that y is the cosine squared of the arc sine of x. The problem with that is it's not very nice. I don't know how to graph that. There's a couple ways you could go here. They're kind of the same, they're a little different. One way is more the trig sub kind of path. We could say, well, sine of t is really x over 1. So then if I draw it like a triangle, and say the opposite is x and the hypotenuse is 1, this third side is the square root of 1 minus x squared. And then cosine of this cosine of t is this over this. Yeah, Dan, that's more what I was thinking. But yeah, so cosine of t is square root of 1 minus x squared over 1. So cosine squared is just 1 minus x squared. But really, what I was actually thinking I wanted to do was say, oh yeah, y is equal to, well, cosine squared of t is exactly 1 minus sine squared of t. And then sine of t is x, so sine squared of t is x squared. You get the same thing either way, but I think it's easier to see it this way. Okay. Oh, and sorry, I forgot my restrictions. Apologies. So first in blue, we'll do that t is between 0 and pi. So let's see what happens. So 1 minus x squared looks like the parabola shifted up 1 and then flipped over. So if I start at t equals 0, when t equals 0, sine of 0 is 0, cosine of 0 is 1. So I'm starting at the point 0. So I'm starting right there at t equals 0. And then when I get to pi, maybe I should go to pi over 2 first. Yeah. So I get to pi over 2. Sine of pi over 2 is 1. So x is going to be 1. So I'm probably going to be right here. Because cosine squared of pi over 2 is 0. So I do this, right? I go this way, this way, this way, this way, this way. I get to the point 1, 0, t equals pi over 2. But then, when I plug in pi, right, I'm going from 0 to pi. Sine of pi is 0. Cosine of pi is -1, so cosine squared is positive. So I'm actually back at this point here. So I go back the other way. So what's happening is we're going back and forth. We go t equals 0 to pi over 2, and then pi over 2 back to pi. And on the other hand, if we let t just go from 0 onwards, so I said t was just greater than or equal to 0, we would still start here. We go here, so we go this way, right? T equals 0 to pi over 2. Then we go back, and this would be t equals pi. And then we keep going this way over here until we get to t equal to 3 pi over 2. Right? Because in times 3 pi over 2, sine of 3 pi over 2 is -1, cosine of 3 pi over 2 is 0. So we're at the point -1, 0. And then we go back this way to 2 pi. So here, if you let time be just any positive number, you just keep going back and forth and back and forth and back and forth forever and ever and ever and ever and ever. You don't get any more of the graph. Yeah. It's especially true, right? So, right, both of these were like parabolas, but one of them you got kind of a whole bunch of it, and one of you just got this little limited part. So it's really important that when you're trying to eliminate the parameter t, you still keep in mind that your functions might limit how big x or y can be, right? We know that since x is sine of t, the biggest it can be is 1, the smallest it can be is -1. And then it is important to be able to parameterize a curve, specifically a line. So this is more important when we talk about lines in three-dimensional space. Because to describe a line in three-dimensional space, you kind of have to use a parametric equation. Basically saying it's going to go through this point and it's going to go in that direction. In two-dimensional space, you don't have to do that, but you certainly can. So let's say I want to parameterize the line segment from the point 4, -1 to the point 1, 7. Which looks like sure. I want to start here and I want to end. Okay. So typically what we do is we find the slope for, do we find the slope? I don't know if we really even need the slope. Here's what we do. We have x of t and y of t. And x of t is going to be some at plus b, and y of t is going to be some ct plus d. For lines anyway. So we know that when time is 0, right, we're going to, or I should say, we don't know. Typically what people do, you don't have to do this way, but it's usually the easiest way, is you say your beginning point of the line is time equals 0, and your end point of the line is time equals 1. So when time equals 0, we want x to be positive 4 and y to be -1. So we're going to let that be 4 and that be -1. And then when time equals 1, we want x to be 1 and y to be 7. So when time equals 1, we want to get x equal to 1. So we want to get 4 plus, we need that to be -3. And when time equals 1, we want y to be 7. So we need to get -1 plus 8 will give us equal to 7. So we need that to be 8. So our parametric equations are x of t is going to be -3t plus 4, and y of t is going to be 8t minus 1, where t is between 0 and 1. And that's a pretty standard way of doing it. Also note, if you wanted the entire line that goes through those points, to get the entire line, you would just say, we're going to let t be between -∞ and infinity. Let's do a couple more, and then we will move on to the more calculus part of things. Let's see, I would like to parameterize the portion of the parabola y equals to x squared minus 2x minus 8 below the x-axis. Okay, that seems kind of funky. Let's see where it hits the x-axis. We set that equal to 0. when you get x minus 4 times x plus 2 equal to 0. So I'm going to get x equal to 4 and negative 2. So those are going to be my x-intercepts. We'll try and graph this thing. Looks kind of like that. And then there's more of it here, right? But I don't want the rest of that. So this is x equal to negative 2. That's an x equal to 4. And nobody told us which way to do it, right? Nobody said we want to start here and end here or start here and end here. So we can kind of make whatever choice we want. So here's the thing. It's really easy to parameterize a curve if you already know y as a function of x or x as a function of y. You just let t be the one that's the independent variable. So in this case, y is a function of x, so we're going to let t equal x. So, or x equal to t, and then y is going to be t squared minus 2t minus 8. And let me ask you guys, you should be able to tell me this. What are the boundaries for t? Well, t is equal to x. So t should be between what and what? Exactly. Right. It's that easy, right? If you already have y as a function of x and you want to parameterize it, it's kind of dumb, but you just let x equal t and then y equal to the same function, but with t's instead of x's. Seems kind of pointless, but yeah. So let's see here. How about the left half of the circle? X squared plus y squared equal to 9. Starting at the top of it, 0, 3, and ending at 0, negative 3. It's looking like this. Okay. So for circles, you typically, I should say, for circles that are counterclockwise, we typically let x equal to r times cosine of t, and let y equal to r times sine of t. And then we just have to figure out kind of where to start and where to end. So, right, I mean, the equation of this circle is given by x equal to 3 cosine of t, y equal to 3 sine of t. And if you started at t equal to 0, you'd be starting right here. So, right, just like on the unit circle, this is angle is 0, angle is pi over 2, angle is pi, angle is 3 pi over 2, angle is 2 pi. So if you use these specific equations, it'll start you here and it will go around counterclockwise. But I don't want to start at t equals 0. I want to start at t equals pi over 2. And I want to end at t equals 3 pi over 2. Sorry, pi over 2 is not 0. Now, what if I wanted to start here and end here? It feels wrong to say you start at 3 pi over 2 and you end at pi over 2, but technically that would be a perfectly legitimate answer. If you don't like that, though, and I probably don't like that, but that doesn't mean it's wrong. It just means I don't feel comfortable with it, but it's totally actually perfectly correct to say you shouldn't write it as t is less than 3 pi over 2 and, or sorry, bigger than 3 pi over 2 and less than pi over 2, because that's not really right. But you can say we start t at 3 pi over 2 and we go to pi over 2. That would be perfectly fine. But another way to do it, if you don't like that, is to essentially make one of them negative. So basically, if I just did x equal to, say, I mean, there's probably at least 2 good ways you could do. You could start here and end here. One way, we could say x equals 3 cosine of t, and y equals 3, sorry, negative 3 sine of t, going from pi over 2 to 3 pi over 2. That would totally work because sine of pi over 2 is 1. So the y coordinate will start at negative 3 times 1, which is negative 3. And the x coordinate will start at 0, which is right there. And then when you get to pi, negative 3 times sine of pi is 0. So you've got right this coordinate here. And 3 times cosine of pi is 3 times negative 1, which is right there. So we're good going that way. Another way you can do this one, though, starting here and going this way, would be, and I'm really just gonna have to work this out. You could start at, you could do x equal to 3 sine of t, maybe negative 3 sine of t, and y equal to 3 cosine of t. Maybe negative. Actually, no. Let's see. I'm really just kind of working it out. Where t goes from 0 to pi. So let's see if this works. I might have to change some of my signs. So if sine, so 0, x is going to be 0, great. I'm starting at the point 0 and negative 3. And y is going to be negative 3 times cosine of 0 is negative 3 times 1, which is negative 3. Cool. And then if I plug in pi over 2, sine of pi over 2 is 1. So I get negative 3 times 1, so I get negative 3 for x. Good. And then plugging in pi over 2 there, cosine pi over 2 is 0, so I get 0. Looks like it works. And then I can plug in pi over 2 to check. Sine of pi over 2 is going to be, sorry, not pi over 2, pi, right? I'm ending at pi. Sine of pi is 0, so I end up with an x coordinate of 0. Great, that's cool. And y is going to be, well, cosine of pi is negative 1, and negative 3 times negative 1 is positive 3, so y is going to be 3. So we're good to go. So the point of this really is there are multiple ways of writing the parametric equations, especially for a circle. You kind of really, my thought process is just you kind of just want to think about it and kind of see if I plug in my starting point, am I starting at the right point? If I plug in like the middle, am I getting the right point? If I plug in the end, am I getting the right point? So if I'm doing a circle, especially, I usually check plugging in like my end point, my middle point, and my end point, just to kind of make sure I'm starting at the right place and ending at the right place. Similarly, if I wanted to do like say the top half of the same thing, x squared plus y squared equal to 9, starting at this point and ending at this point. Well, again, there's a number of ways you could do that. I usually try to start at time equal to 0 if I can. And since I'm doing half a circle, it's probably going to be pi's worth of time, right? Half of a 4 evolution angle-wise. So let's see. I need x to start at negative 3. So I probably need x to be negative 3 cosine of t. Just going to plug in 0. I'll get negative 3 times cosine of 0, which is negative 3 times y. And I need y to start at 0. So y could be either 3 sine of t or maybe negative 3 sine of t. But I think it's positive 3 sine of t because I want my y values to be positive. So like when I plug in pi over 2, I'm going to get x to be negative 3 times 0, and y is going to be 3 times 1, and I am going to get the 0.03. So we're looking good. And then when I plug in pi, x is going to be negative 3 times negative 1, which is 3. Y is going to be 3 times 0, which is 0. So we're good. And then there's a homework problem that asks you to do one like this, but it's actually like shifted over. So it's actually like this. Instead of going from negative 3, 0 to 3, 0, it's going from 0, 0 to like 6, 0. Right, you're basically just shifting that whole thing 3 to the right. Well, that's actually super easy. You take this thing here and you shift your x values 3 to the right. Not too bad at all. there's a homework problem similar to that. All right, let's look at some calculus with parameterized curves. And this graph, so there's definitely a question on your homework. It's kind of like this, where you have to like find the area inside the loop of something. We're definitely going to do that with this one. And I feel like the function I have is not quite exactly the same, but it's very similar to the function you have. So here is the curve I'm going to look at. We've got x is equal to t squared, and y is equal to t cubed minus 3t. I think the ones I've seen in the homework is like x equals 9 minus t squared, and y is like 4t minus t cubed. It's very, very similar, but not exactly the same as this. So for a curve like this, you could try eliminating the parameter. It's not totally unreasonable. If we do eliminate, so I want to show you because it's not great. I could solve for t here. Well, so t equals plus or minus the square root of x. Okay. So when t is positive, then t is equal to the square root of x. And then I plug that in here, and I'm going to get y equal to x to the 1/2 cubed, so x to the 3/2, minus 3x to the 1/2. That's not very nice. And then when t is less than 0, we're going to get t equal to the negative square root of x. Sorry, yeah, that's right. And then y is going to equal the negative square root of x cubed, which will, when you cube a negative, it's still negative. So you're going to get negative x to the 3/2 plus 3x to the 1/2. We can look at this graphically. So I want to emphasize here that while this is possible sometimes, it is often not possible to eliminate the variable t from your stuff. So we do have some equations. Excellent. Let's go ahead and look at Desmos just to kind of see what they look like. Let's share my screen. Share it up. I wish you. Okay. Yeah. So let's look at these. So we've got y equal to x to the 3/2, 1.5, minus 3x to the 1/2. And then we've also got the negative of that. Let's just copy that, paste it, and then do a negative there. So there's our curve. And so, right, the first one, when this one here, so this is when t is positive, and this is when time is negative. So basically, we're starting like down here when t is really negative, t is less negative, t is less negative, t is less negative, t is something here when y is 0. And then up to here, we're getting t equal to 0 right there. Because when time is 0, x is 0 and y is 0. And then we're moving into t being positive. So if you were to trace this one out, as time moves forward, you're starting here and you're going this way. It's kind of cool. I hadn't actually done this before, so it's kind of neat. But a lot of the times we're not going to be able to graph the things. At least we're not, I should say, not that we can't graph the thing. We're not going to be able to solve for t as a function of x or y and plug it in easily to the other equation. For example, if that was x equal to t squared plus t, we'd have a much harder time doing this. Still not impossible, but it starts to get messy. But what we can do, and what we should do, is we should plot some points. It's a good idea to kind of try to see what's happening here. So I know I said we don't always want to do this, but sometimes it's kind of the best. So especially because like graphing the things I graphed down on Desmos, I wouldn't really be very good at graphing those equations on my own, right? Like if I was trying to graph, what was it? I was trying to graph y equal to x to the 3/2 minus 3x to the 1/2. I mean, I do an okay job, but I wouldn't do a great job, I'm not gonna lie. But let's go ahead and just try and find some points. So let's start like, let's do like t going from -3 to +3. And one of the reasons I picked those values specifically is because I can see that this function is even, right? If you pick a negative or a positive number, you get the same result. This function is odd, right? If you pick a negative number, you're going to get something. Pick the corresponding positive number, you're going to get the opposite value. So when time is equal to -3, x is going to be 9, and then -2 is 4, and then 1, and then 0, and then 1, and then 4, and then 9. So the negative values and the positive values have the same corresponding output. And then y, which is going to be t squared times t minus 3, right? T times, well, that's not right. That is not right. It's going to be t times t squared minus 3. You plug in -3, you're going to get -3 times 9 minus 3, which is -3 times 6, which is kind of large. It's all right. Let's see. -3 times 6 is -18. When you plug in -2, you're going to get -2 times 4 minus 3, which is -2. When you plug in -1, you get -1 times 1 minus 3, which is negative. So +2, and -1 times, yeah, +2. You plug in 0, you get 0. And then all these should be the opposite sign. So when you plug in 1, you get 1 times -2, which is -2. You plug in 2, you're going to get 2 times 4 minus 3, which is 2. You plug in 3, you're going to get 3 times 9 minus 3, which is 18. So let's try plotting this. So let's see. I'm only looking at these, and let's maybe not graph those ones. So I'm going to get the point. So let's see. I've got the point x is 4, y is -2. And then I've got the point x is 1, y is +2. Okay, that's a quick change, right? So I'm going from 4 -2 to 1 +2. Okay, so I'm going from there to there, and then I'm going to the point 0, 0. Sorry, so here's time equals -2, time equals -1, time equals 0, and then I'm going to the point 1, -2. That's time equals 1, and then to the point 2, 4. So I'm going this way, I'm going to hit that point, I'm going to hit that point, that point, that point. So let's do something like that. And these are probably crossing each other actually on the x-axis. Okay. Sure. Yeah. We could find that point if we wanted to by setting y equal to 0. So we set y equal to 0, we get t equal to 0, but we also get t equal to the plus or minus square root of 3. And when t equals plus or minus square root of 3, x equals 3 or 3. So this point here, which is the point 3, 0, is when t is equal to both positive root 3 and negative root 3. And kind of the place where the function crosses itself is where your loop is going to start and end. Yeah. Okay. So now we need to do a bunch of calculus. So we want to ask some questions like, what's the derivative? What's the second derivative? When does the function have a horizontal tangent? When's the function have a vertical tangent? So I'm going to erase this part here. So when do we have a horizontal tangent? So we're really asking the question, when is the derivative equal to 0? So we want to know, when does dy dx equal 0? Well, we don't have y as a function of x. What are we going to do? Well, we could, although we're not, because you can't always do it. We could do the thing where we had, y equal to x to the 3/2 minus 3x to the 1/2. You could take the derivative of that and set it equal to 0. But again, that's not always going to be an option. It's really, really not the point of this section. What we should do is we should use the parametric derivative formula, which comes from the chain rule. So we have y as a function of x, or at least we are thinking of y as a function of x. But x is a function itself of t. So we can think of, we have y of x of t. And if we take the derivative of that, y is a function of t, it's going to equal, we know the chain rule, it's the derivative of the outer function, leave the insides alone, times the derivative of the insides. Okay, but let's use some different notation here. This here, this is the derivative of y as a function of t. This is dy dt. And this is equal to the derivative of y as a function of x. And because you're saying you have y prime and leaving the inside alone, you're kind of just seeing that as an x. So that's dy dx times dx dt. So I'm going to solve for this. And we get dy dx is dy dt divided by dx dt. So, and this is an important formula for parametric derivatives. Dy dx is dy dt divided by dx dt. So whenever we're finding derivatives of parametric equations, if you want to find dy dx, you have to find it as dy dt divided by dx dt. Yeah, okay. So now I'm asking, when do I have a horizontal tangent? So when is the derivative equal to 0? Well, let's find the derivative. Dy dx is equal to dy dt, which is 3t squared minus 3, divided by dx dt, which is 2t. So I set that equal to 0. I'm really just setting the top equal to 0. So I'm setting 3t squared minus 3 equal to 0. And I'm going to get t equal to plus or minus 1. Right? 3t squared equals 3, t squared equals 1, t equals plus or minus 1. Which means I'm going to get the points. When t is 1, I'm going to get x equal to 1, y equal to 1 minus 3, which is negative 2. And I'm also going to get x equal to negative 1. Oh, sorry, positive 1 again. Sorry. When t equals negative 1, I'm going to get x equal to 1. I'm going to get y equal to negative 1 plus 3, which is positive 2. So this point here, when t equals negative 1, I'm at the point 1, negative 2, and there's a horizontal tangent. And when t equals 1, I'm at the point, 1 comma negative 2. This was 1, 2. Apologies. I have a horizontal tangent. So that's where my horizontal tangents are, where the derivative is equal to 0. All right. Yeah. Let's just go to the other side. Turn on the AC in here, it's getting a little warm. Okay, so let's draw a picture again so we have it. And again, we have x equal to t squared, y equal to t cubed minus 3t. And we just found that dy dx was equal to 3t squared minus 3 divided by 2t. And now I'd like to ask, where do we have a vertical tangent? Okay, well, we have a vertical tangent where the derivative is undefined, right? So what am I trying to say here? a vertical tangent, right? The tangent line is a vertical line, and the vertical line has an undefined slope. So we need the derivative to be undefined, like divided by 0. So we're gonna have a vertical tangent when the denominator is equal to 0. When t equals 0, which is at the point 0, 0, because if t equals 0, x is 0 and y is 0. So we have a vertical tangent right there. All right. Let's ask about the concavity. So again, I'm going to remind everybody, right here is where t equals -2, t equals -1, t equals 0, t equals 1, t equals 2. So it looks to me that from here all the way to right here, it seems to be concave down. Like it's opening in a downward way. Whereas from t equals 0 onwards, it seems to be concave up. So I would expect it to be concave down when t is negative, to be concave up when t is positive. And the way we tell if a function or a curve is concave up or concave down is if the second derivative is positive or negative. So we know it's going to be concave up if the second derivative is greater than 0. It can be concave down if the second derivative is less than 0. Okay, but how do we find the second derivative? Well, it's a little bit tricky. I'm going to do it this way. So we know that dy dx is equal to dy dt divided by dx dt. And let's call this y prime, or even better, let's call it f for a second. So now I want to find the second derivative. I want to find d squared y dx squared, which if I'm calling dy dx, so which is the derivative of the derivative. And I'm going to write this, and this is where if you have questions, you really should ask them. I'm going to write this as the derivative of just f, or df dx. Okay, but here's the deal. F, right? F is the derivative. And f, just like y, f is a function of t, just like y is a function of t. And so just like I said before, that dy dx is dy dt divided by dx dt. It is perfectly legitimate and the only way to find that df dx is in fact df dt divided by dx dt. I'm just using the same idea as I used before, that if you have if y is a function of t and x is a function of t, then dy dx is the derivative of y with respect to t divided by the derivative of x with respect to t. Same idea here. F is a function of t, x is a function of t. df dx is the derivative of f with respect to t divided by the derivative of x with respect to t. I said the same exact words, I just used f instead of y. Okay, but now we can deal with df dt. Because df dt, yeah. So I'm going to write df dt as d dt of f over dx dt. But then f is really dy dx. This is really the derivative with respect to t of whatever you found for dy dx divided by dx dt, which is totally doable. So here's what we're going to get for the second derivative. I'm going to erase this. So our second derivative, d squared y dx squared, is going to be d dt of our dy dx, which is this gross thing here. 3t squared minus 3 over 2t divided by dx dt, or d dt of x. right? That's your dy dx. That's your x. Are there questions about this? All right, I would rather not use the quotient rule if I don't have to. So instead of using the quotient rule here, I'm going to erase the graph, right? We know from the graph it should be concave down when t is negative and concave up when t is positive. I need some more room though. So it's this. It's this. So let's see. So I'm going to rewrite this as the derivative of 3t squared divided by 2t is just 3/2 t. And negative 3 divided by 2t is negative 3/2 t to the negative first. To be a little bit easier to differentiate. Divided by the derivative of t squared, which is just 2t. So we end up getting 3/2, right? The derivative of 3/2 t is 3/2, and then minus 3/2 times the derivative to the negative 1 is going to be plus 3/2 t to the negative second, all divided by 2t. That seems good. Notice this is never equal to 0. In fact, we can make this even nicer. Let's factor out a 3/2 left with a 1 plus t to the negative second, which is 1 over t squared, all over 2t. If you really wanted to, and I probably would, I would probably make the call to multiply the top and the bottom by t squared. So I'd have 3/2 times t squared plus 1 over 2t cubed. To me, that just feels nicer. Again, probably not super necessary. When is this equal to 0? It's not. The numerator is never 0, so the whole thing is never 0. Great. So when is it negative? That's right. Well, I know it's undefined when t is equal to 0. And then I know if t is positive, pick something positive, top's positive, pick something positive, bottom's positive, the whole thing's positive. So it's concave up when t is positive, just like we said it would be. And then when t is negative, the top is still positive, but the bottom is negative. So now it's negative over here. So it's concave down, just like we said it would be. So it's concave down when t is less than 0. It's concave up when t is greater than 0. Okay. I would like to find 2 more things. Well, I'm going to talk about finding 2 more things. One of them might totally suck. One of them might not. So I would like to find the area enclosed by this loop. And there is a formula for that. Well, in fact, it's the formula you get. So really, it's the formula you already know, kind of. So if I want to find the area enclosed by a curve, y as a function of x, the area enclosed by y is just the integral over some limits of integration of y as a function of x times dx. And of course, we don't really have y as a function of x. I mean, y is a function of x, but it's also a function of t, because x is a function of t. So what we're going to do is we're going to say, well, sorry, let's just, maybe y of x is a little too bold there. Call it y. Yeah. We're going to replace things with t's. We can say that y is in fact y of t. And dx, well, I know that dx dt times dt is equal to dx. So this can replace that, but dx dt is just x prime of t dt. So what we're really going to do to find the area enclosed by this loop is we're going to do the integral from, instead of x equals a to x equals b, we're going to do it from some t equals alpha to some t equals beta. It's essentially the corresponding time values for those x values. And we're going to do the integral of y of t times x prime of t dt. It seems a little like we're just making stuff up here. It kind of feels that way, but we're not. It's totally legitimately valid. So let's see what happens. So I don't want to erase my picture, but I'm kind of out of room. So we're going to go from, I think, so I'm worried we might have to break this up into two pieces. I'm not positive because, let me just draw my picture again over here real quick, right? It does this kind of, right? It does this kind of deal where at that point there, so right here's t equal to -2, here's t equal to -√3, and then all the way over to t equal to 0, and then all the way over to t equal to √3. There definitely should be a positive amount of area, right? There's definitely a non-zero amount of area enclosed there. But I feel like if we do it, I feel like if we don't break it up, something weird's going to happen. But let's see what happens, because I'm actually not sure. Let me see. Actually, there is one thing I should look at. Okay. So there is something that you should know, and I think this will kind of clear it up. When you integrate, we still should integrate from left to right, which I know sounds funky. So, yeah, I'm a little, let's just see what happens when we go from -√3 to √3. I feel like it's going to come out negative. So I want -√3 to √3. My y function, if you recall, the y function was t cubed minus 3t. And the derivative of the x function was t squared, so x is going to be 2t, x prime is going to be 2t. Right, again, y was t cubed minus 3t, x is t squared. So let's see what happens. I'm a little nervous, but we'll find out. I feel like it's going to turn out to be negative. So I'm going to go from -√3 to √3 of 2t to the 4th minus 6t squared dt. We're going to integrate that. It is an even function. We could totally do it as double the integral from 0 to √3 of 2t to the 4th minus 6t squared. That might be better. I feel like this, I don't know. I'm curious how this is going to come out. So we're going to get 2 times 2t to the 5th over 5 minus 6t cubed over 3 from 0 to the square root of 3. And then that's going to be 2 times, let's factor out a t cubed. No, let's not. Sorry. So this is a 2/5 square root of 3 to the 5th minus 2 square root of 3 cubed. And what is that? Good question. Let's factor out a few things. So we can factor out a 2. So we have a 4. We can also factor out a square root of 3 cubed. So a square root of 3 cubed. And we're left with a 1/5 times a square root of 3 squared minus a 1. Because I factored out a 2 and the square root of 3 is 1/3. Yep. And look, our answer is negative. So We get 4 times the square root of 3 cubed times 3/5 minus 1, which is -2/5. So what happened here? Why did we get a negative answer? Well, here's why. So for this part here, for this portion of the curve, right, when we go from t equals -2, t equals -√3 to t equals 0, we have to integrate from left to right, meaning we actually need to do the integral from 0 to -√3 of our y of t times x prime of t dt. And then from here to here, we would do the integral from 0 to +3, except if we do that, since the area is under the x-axis, is going to come out negative. So we want to add the negative of the integral from 0 to +√3 of the same function. Well, yeah, we can change the order of integration here. So we can make this a plus. And then putting these together, it is the integral from √3 to -√3 of the same function, which is not what we did, right? We did the other way. So it's kind of screwed. Basically, when you're integrating parametrically, you have to look at which t is more to the left and which t is more to the right. And the most left one is your lower limit, and the most right one is your upper limit. So if I was just trying to find, it might have made more sense to just talk about finding this area in green. If I wanted to find that area in green, it would definitely be the integral from t equals 0 to t equals -√3 of whatever our function was, y of t times x prime of t. Interesting. Kind of weird. No doubt about it. Yeah. Let's see what else we got here. Finding equations of tangent lines is actually not terrible. You guys doing all right? Hanging in there? I know it's a long class. So find the equation of the line tangent to x equal to t to the 4th plus 1, y equal to t cubed plus t at t equal to 2. We could totally do this parametrically if we wanted to, although that's really kind of not the point. So finding the equation of a tangent line is your usual stuff. Find the slope, find the point, and then you're going to do y minus the y point equal to the slope times x minus the x point. That's really kind of all there is to it. So, except it's a little more complicated because we have to find our derivatives parametrically now. So our point, before we even find the derivatives, our point is just going to be x equal to 2 to the 4th plus 1, which is 17. And y is going to be 2 to the 3rd plus 2, which is 10. So the equation of our line is going to be y minus 10 equals whatever our slope is times x minus 17. Now we just have to find the slope. So we need to find the derivative. dy dx is dy dt divided by dx dt. dy dt is going to be 3t squared plus 1 dx dt is going to be 4t cubed. So plugging in t equal to 2, so the derivative at t equal to 2 is going to be 3 times 2 squared plus 1 over 4 times 2 cubed, which is going to be 12 plus 1, so 13 over 4 times 8, which is 32. And then if we have to solve for y, we just add a 10 over. So y equals 13 over 32 times x minus 17 plus 10. And then I guess if you wanted to, you could multiply that. It's kind of gross though, right? You're going to get y equal to 13 30-seconds x, and then 13 times 17 is 221. So it's minus 221 over 32 plus 10, which is 320 over 32. So you're getting y equal to 13 30-seconds x plus 99 30-seconds. That just seems silly, right? Plus, I'm pretty sure Desmos will take, or not Desmos, I'm pretty sure WebWork will take that. So why do more work than we really have to? All right, let's see, what else have we got here? I'm curious, but I don't actually know if it's going to turn out to suck or not. So let's start it, and then if it looks like it's going to be terrible, we will abandon it. But so there's like 4 things you get. There's 4 calculus things we talk about with parametric equations. First derivative, second derivative, area, and then there's also the length of a curve. So I could ask, and it might be a terrible question, but I could ask, how long is this part here? We're going to use the arc length formula. So the arc length formula is equal to the integral of ds. So remember the old ds? The square root of 1 plus the derivative squared, or the square root of 1 plus the other derivative squared, or parametrically, the square root of dx dt squared plus dy dt squared dt. That's the arc length formula using parametric equations. And let's remind ourselves what these equations were. Y was equal to, I don't remember what y was equal to. I think it was, I know x was equal to t squared, y was equal to t cubed minus 3t, I believe. That seems wrong. Let me double check that just to be absolutely sure. Nope, that's right. Okay. Not losing it. So I feel like this is going to be awful. Well, let's check it out anyway. So to find the arc length, I probably need to go from left to right. I bet, although I'm not 100% positive, but I'm pretty sure I need to go from 0 to negative square root of 3. The nice thing about these is if you do it the wrong way, it's really easy to fix. You just change the order and then change the sign of your answer. So we're going to do the integral from, I'm pretty sure, 0 to negative square root of 3 of the square root of the derivative of x quantity squared. So it's going to be 2t quantity squared plus the derivative of y quantity squared. So that's going to be, I'm already pretty sure this is not something we want to do. 3t squared minus 3 quantity squared. And that looks like it's probably going to be pretty impossible to deal with. Yeah. What I was hoping for, which was a real long shot, was you'd have the kind of thing where you square this out and the middle term is the opposite of that. So if we did this here, right, we'd have the square root of, this is 4t squared. If you multiply this out, you get 9t to the 4th minus 3 times 3 is minus 9t squared twice. So minus 18t squared plus 9. So what I needed to be true was I needed this to, instead of being 4t squared, I needed that to be 36t squared. So let's change our function. Yeah, we can do that. I need my derivative to be 6t. So let's say we have that. So that's it is a different function. So I don't exactly know how it looks. I'm changing things too much, probably. It's not that different. I don't feel, no, I think we're still pretty okay, actually. Because I still think we actually, so I think we're actually really okay. So check this out. If we do this instead of t squared, we still get t equal to √3 and negative √3 as where the things cross each other, right? Because at t equals negative √3, y is still the same, y is still 0, and x is going to be 3 times 3, which is 9. And t equal to positive √3, y is going to be 0, and x is going to be 9. So we just shifted this out. Instead of this being at the point x being 3 and y being 0, now that's the point where x is 9 and y is 0. But it's still a valid thing. So let's do this. So our dx dt now, instead of being 2t, is 6t. And 6t quantity squared is 36t squared. Integral from 0 to √3 dt. And now look, when we add the 36t squared there, we get the integral from 0 to √3. Sorry, I changed that from 0 to negative √3. I'm still not exactly sure about that. The square root of 9t to the 4th plus 18t squared plus 9. Okay. Then that's exactly going to be the integral from 0 to negative √3 of the square root of 3t squared plus 3 1 squared. And then the square root of that is actually the absolute value. So it's equal to the integral from 0 to negative √3 of the absolute value of 3t squared plus 3. But that's always positive. We don't need the absolute values. I'm really hoping this turns out to be positive, but it might turn out to be negative. Let's see what we get. We get t cubed plus 3t from 0 to negative √3. It turns out to be 0. I'm going to be very upset. It turns out to be 0. Yeah. No, it's not 0. It turns out to be negative. Okay, that's less upsetting. So I'm going to get negative √3 cubed plus 3 times negative √3, which ends up being negative 3 √3 minus 3 √3, which is negative 6 √3. But it should be positive because it's an arc length, so do it the other way, make it positive. I'm curious. What does the book have to say about this? Okay, so I was mistaken. So the book specifically says in the definition here, if you have a curve defined parametrically where x is one thing and y is another thing, and blah, 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 and the curve is traversed exactly once as t increases from t equals a to t equals b. So for arc length, t should just always go from lowest to highest. It doesn't matter if it's left or right. For area specifically, it needs to be left to right. But for arc length, I guess it doesn't matter. So we totally should have done this one as negative √3 to 0 instead of 0 to negative √3. It's good to know. I learned something. And if we had done it that way, then it totally would have worked out the way it was supposed to. Because then we would have gotten, instead of getting this, we would have gotten 0 minus that, which would have been made it positive. So if we have 0 minus this, it's going to be plus this, plus this, plus this. Okay. So for arc length, you just make sure you go from a lower t to a higher t. But for area, you do have to make sure you go from left to right. Let me show you another example of area being left to right. Yeah. See, where's my other example here? The legs feeling kind of funky. Need to do some stretches. Okay. So let's see here. Let's look at this one, which is pretty not terrible. Let's find the area under x equal to cosine of t, y equal to t squared for t between 0 and pi. Let's graph it. So we know that cosine of 0 is 1, cosine of pi is -1. So the graph of this is going to start, well, at t equals 0, we're going to get the point 1, 0. And then at pi over 2, cosine of pi over 2 is 0, so x is going to be 0. And y is going to be pi over 2 quantity squared, which is like a little bit more than 2. And then when t is pi, cosine of pi is -1. And pi squared is like bigger than 9. So it really kind of gets super big here. So let's do something like this. My picture is not great. Sure, fine. The picture is awful. Let me try. Yeah. Sorry, picture is bad. Okay, sure. So this is the point -1 comma pi squared when time is equal to pi. Here's the point 0 comma pi squared over 4 when time is equal to pi over 2. And here's the point 1 comma 0 when time is equal to 0. So as time increases, we move from right to left. If you want to find the area, which again is the integral of y of t times x prime of t dt, we have to make sure we go from left to right. Left to right is going to be time equals pi as the lower limit to time equals 0 as the upper limit. So it's going to be the integral from pi to 0 of y of t, which is t squared, times the derivative of x of t, which is negative sine of t. And hopefully already you guys can see that this is right. Because if I did it the other way, well, sine of t is positive in the first and second quadrant from 0 to pi, which means negative sine of t is negative, which means this whole function is negative. And if you integrate a negative function, it's going to turn out to be a negative answer. So that's a good way of seeing that, oh yeah, this is not right that way. It's got to be like this. In fact, if you wanted to, you could totally do the thing where you lose the negative and you switch your limits of integration. So you can totally say just with integral rules, that this is equal to positive integral from 0 to pi of t squared times positive sine of t. And that's totally going to come out to be a positive answer. Let's go ahead and find it. We know how to integrate this. I'm going to use tabular. So my integration by parts, my u is going to be t squared. Right, and then the derivatives are going to be 2t, 2, and 0. And my dv, that's not, I don't want a dv, that's my u. My dv is going to be sine of t, and the antiderivative is negative cosine of t. The antiderivative is negative sine of t. The antiderivative is cosine of t. It's plus this times this, it's minus this times this, it's plus this times this. So this is going to end up equaling negative t squared cosine of t minus 2t times negative sine of t, so plus 2t times sine of t plus 2 cosine of t from 0 to pi. And then that's going to end up being negative pi squared times cosine of pi, which is negative 1, plus 2 pi times sine of pi, which is 0, plus 2 cosine of pi, which is 2 times negative 1, minus 0 squared is 0, plus 2 times 0 is 0, plus 2 times cosine of 0 is 2 times 1. So we end up getting pi squared minus 2 minus 2, which is pi squared minus 4, which is certainly positive. So yeah, when you're doing these, so basically what you should really do is try to get it right from left to right. But if you mess it up and it comes out negative, change them, change your answer, right? It's not hard to fix. Yeah, let's see what else have I got here. I have something else to say. Maybe not. So here's what I would say. I'm kind of out of material, to be perfectly honest, but there is a handout with more problems. So if you're looking for extra work to do, which I'm sure you all are or not, it's perfectly fine either way. But on Grant's website, there are a couple of handouts. Let me give you the links to them. Obviously, you know how to find Grant's website as well. I imagine I've mentioned it many a time. So there's some parametric problems, and here are the solutions to them. But for the last 20 minutes of class, I don't really have much to say. If you have questions you want to ask, I'm certainly happy to address them. Or we can all just call it a day. Whatever you guys want to do. If you have questions, take a minute. Can we do 15 on Professor Schulten's homework? Let me take a look at it. Other people are welcome to ask questions as well, whether from the homework or from other places. Homework. Is that homework not 8 or homework 9, Katie? I'm assuming
it's homework 8.
Okay. I wonder what's on home. Now I'm curious about what's on home. I'm also going to look at homework 9 just because I'm curious now. Oh, it's probably not available yet. Yeah, it's not. Lame. Don't do that. Okay, give me the homework, you foolish thing. That's not what I want. Okay, there we go. Problem 15. Find the area of the surface obtained by rotating the curve. Oof. Whew. Surface area. I feel like I saw that somewhere and then I kind of forgot about it. Okay, that's what I assumed it would be. All right, let's do, so actually, this is probably, before we address this particular question, it's probably worth me doing an example. It's not that. But yeah, I don't think, oh no, we get, okay, cool. I've got a couple, all right. So let's do some surface area problems and then we can talk about problem 15. So surface area is going to be just like how arc length was the same except different. So we know in general, it's red, sure, it's a red kind of day. Good call, Katie. I'd forgotten surface area was the thing we did parametrically. So surface area, very generally, is the integral of 2 pi r ds. And so when we were doing this with y as a function of x or x as a function of y, and so if you had like y as a function of x, you would get the surface area to be the integral of 2 pi times, well, it depends on what axis you're going around. So if you have y as a function of x and you're going around the x-axis, you could either, well, you would do it as the integral of 2 pi times the radius, which is y, which is f of x, times your ds, which is the square root of 1 plus f prime of x squared. That would be one way of doing it. Right, so there's your radius, which is y equal to f of x. Because again, if you're going around the x-axis, your radius is y. And then there's like a freaking billion ways to do this, right? If you were, you could also, if you had x as a function of y instead, then the surface area would be the integral of 2 pi times y times the square root of 1 plus g prime of y quantity squared dy. You know what the nice thing about parametric equations are? Whatever we do, we're going to have to use t's. So we really just have to think about what's happening. I know that seems like a no, like an obvious thing, but like, of course, we just have to think about what's happening. But I think you know what I mean, right? You have to think about what axis we're going around, what's our radius. So here is a problem. Let's look at this one, which I don't think is terrible. I've done this one before, and I feel like I missed something. So let's see. Let's say we've got x is cosine cubed of t, and y is sine cubed of t. And t is between 0 and pi over 2. And we're going around the x-axis. I want to know the surface area. So I don't know what this looks like exactly, but it probably looks something like, well, let's see, x is going to start at 1, y is going to start at 0. And then at pi over 2, x is going to be 0 and y is going to be 1. Probably like something weirdly like that. I don't know exactly. I'm going to rotate this around the x-axis. I'm going to get some shape that's going to look vaguely like that. Some like half of a bowl or something. So we need to think about what our ds is. Well, ds actually is never an issue. Parametrically, ds is always going to be the square root of dx dt squared plus dy dt squared. Okay, let me ask you guys, for this problem, going around the x-axis, is my radius x or is my radius y? Perfect. My radius is sine cubed of t. Right. My radius is y, but it's always going to be in terms of t. So here my surface area, being the integral of 2 pi r ds, is going to be the integral of 2 pi times sine cubed. I need more room. Times ds, which is the derivative of this squared plus the derivative of this squared. Okay, the derivative of cosine cubed is 3 cosine squared times negative sine. Quantity squared. And the derivative of sine cubed is going to be 3 sine squared times cosine. Quantity squared. So the nice thing about doing surface area parametrically is it all boils down to t pretty fast. And I believe we don't have to worry about left to right, right? Because it's just like our surface area is like arc length, not like area. So, right, which that sounds wrong because you're talking about surface area. Oh. I think, let me. No, yeah, it says the same thing in the book. It says t increases from A to B. So we should go from t equals 0 to pi over 2. All right, so now I have to simplify this garbage. So let's see what happens. We end up with the integral of 2 pi times the integral from 0 to pi over 2 of sine cubed square root of, let's see, I've got a not, so there's a 9 here and a 9 here. I can factor out a 9 and square the 9 is 3. So let's factor out a 3. And then I'm left with a cosine to the 4th, a sine squared, plus a sine to the 4th times a cosine squared. And from each of these, I can factor out a cosine squared times a sine squared. So I'm left with integral from 0 to pi over 2. I suppose I can make that a 6 pi. Again, the rest of this really isn't so much the point. The point is setting it up, but it's worth going through it. So I get a 6 pi sine cubed of t. I can factor out a cosine squared of t times a sine squared of t. And I'm left with a cosine squared plus a sine squared. That often happens where that trig identity shows up. That's just equal to 1. The square root of cosine squared is cosine, the square root of sine squared is sine. I don't need absolute values because I'm in the first quadrant where both of them are positive. So I end up with 6 pi integral from 0 to pi over 2 sine cubed times another sine times cosine. So sine to the 4th times cosine of t. Then we can do a u sub. We would let u equal sine, du would be cosine of t dt. So this would become 6 pi times the integral of u to the 4th du. If u is sine, sine of 0 is 0, sine of pi over 2 is 1. So we end up with 6 pi times u to the 5th over 5 from 0 to 1, which is going to be 6 pi times 1/5. Good times. Let's look at another example. I want to do that one. That one looks like it might be all right. Let me look in the book here. Sure. Let's do one around the y-axis. Yeah. I'm going to go one in your homework before I get too carried away here. Come on. Yeah, we could look at the one in the homework. Why not? Here's what I've got from the homework. I feel like this homework problem is like they took something and just multiplied it all by 8. So here's what I've got. I've got x equal to 8t minus 8/3 t cubed. And I've got y equal to 8t squared. Okay. And t is between 0 and 1. So to set up the surface area integral. Okay, that's all right, Caitlin. That said, I still think it's worth doing this problem because I think it's worth practicing. Yeah. And actually, so let's actually talk about the difference between around the x-axis and around the y-axis. So we'll set up both of them. So we'll go around the x and we'll go around y. And before we do either, it's probably going to be worth our time to find ds. So again, remember, ds is always just, well, parametrically, the ds is just the square root of dx dt squared plus dy dt squared. I suppose technically I'm leaving off a tiny bit. It's the square root of dx dt squared plus dy dt squared times dt. We should have that as well. So in this case, it's going to be, now our expectation is that this should simplify relatively nicely. Something nice should happen. Let's find out. So I'm going to get the square root of this derivative squared. So the derivative of this is 8 minus the derivative of 8/3 t cubed is 8/3 times 3t squared, which is 8t squared, quantity squared. And then the derivative of y is going to be 16t quantity squared. And I would probably bet my life that as long as I didn't make a mistake, that when you multiply this out and add this, you're going to get the middle term switching signs. Let's see. Now I'm like, yeah, it should work out. Let's see, multiplying this out, we get 64. And then 8 times negative 8t squared is negative 64t squared times 2. So negative 128t squared plus 64t to the fourth. And this is 16 squared is 256, which is exactly twice that. So this becomes the square root of this There's a little more room. This is going to be the square root of 64 plus 128t squared plus 64t to the fourth, which is exactly the square root of this with a plus sign squared. So 8 plus 8t squared. Great. So now around the x-axis, the surface area is the integral of 2 pi r ds, which in this case around the x-axis means that r is going to be y. So we're going to get the integral from 0 to 1 of 2 pi times y, which is 8t squared, times ds, which is 8 plus 8t squared. That's not terrible. That would be 2 pi integral from 0 to 1 of 8t squared times 8, which is 64t squared, plus 8t squared times 8t squared, which is 64t to the fourth. Totally manageable. I think all of you could handle that, no problem. If it was around the y-axis, I also think you could all handle it. So if we're going around the y-axis, well, then our radius is x. So the surface area is going to be the integral from, again, 0 to 1, because t is still going from 0 to 1, of 2 pi times our radius, which is now x, which is 8t minus 8/3 t cubed. Right, that's our radius, which is x, times this, which is, again, 8 plus 8t squared dt. It's a little bit worse, but not like terribly. You're still just multiplying this out and then anti-differentiating and plugging in 0 and 1. The numbers might not be very nice, but they're not particularly terrible here. Yeah, good question. Thank you for asking it. I appreciate it. I had completely forgotten about surface area.